I am Dr. Himamaheswara Rao, Assistant Professor of Physics, Department of Good morning. I am Dr. Himamaheswara Rao, Assistant Professor of Physics, Department of Freshman Engineering, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Welcome to the lecture series Atomic and Molecular Spectroscopy. Today we are going to discuss vector atom model, electronic structure of the atom. It is the part 2 of the continuation to the earlier lecture. So, vector atom model, in our earlier lecture, we discussed the different rules defined by the vector atom model in order to filling of electrons in different orbitals inside an atom. So here we discuss some more rules followed by vector atom model in order to fill the electrons in different orbitals. So the basic rules followed by vector atom model are here. First one is minimum energy condition. So electrons tend to occupy the lowest available energy state such that their total energy is minimum. So if there are some certain number of electrons, all the electrons try to occupy the lowest energy states, available energy states. So that means they go to higher energy states only when the lower energy states are not vacant. So first they fill the lowest energy states. So whenever the next filling next electrons, when they try to occupy the lowest energy states as they are already filled, they occupy the next energy level, next higher energy level. So this is so that means electrons while filling in the orbitals they follow they try to occupy the minimum energy level. And the second rule is Pauli's exclusion principle. So in general, an orbital in an atom is described by quantum numbers such as principal quantum number, orbital quantum number, and azimuthal quantum number. And there could be two electrons having the same values of all these quantum numbers, and those two electrons also can have opposite spin directions. That means ms value for one electron will be plus 1 by 2, and for the other electron it should be minus 1 by 2. That means no two electrons can have all four quantum numbers same. All four quantum numbers means N, L, Ml and Ms. Even two electrons can have these three quantum numbers the same, but the fourth quantum numbers Ms must be different. For one electron it should be 1 by 2, for the other electron it should be minus 1 by 2. So that is the Pauli's exclusion principle. And then the third basic rule is Hund's rule. So according to this rule, the order of filling of the orbitals of subshells obeys Hund's rules. So while filling the subshells, we need to follow the Hund's rule. According to this rule, the total spin number of the electrons of a shell must be maximum. Total spin number of the electrons of shell must be maximum. So by following this, that means the orbitals of the subshells are filled first with one electron, and then if there are still more number of electrons, we come to fill second electron in those subshells. For example, if we consider nitrogen atom in general, the nitrogen atomic number Z equal to 7 for nitrogen atom. So while filling the orbitals, generally we come like this: 1s2, 2s2, 2p3. That means 3 electrons occupy the p shell. Here also there are subshells. Subshells here like this: 3 subshells. So while filling, these are px, py, pz. So while filling these subshells px, py, pz, first it will not occupy px and py. So first each, one electron occupy px, another electron occupy py, and one more electron in the pz subshell. Okay, so like this. So it should not be like first 2 electrons in the px and 1 electron in the py. So first subshell is filled with 1 electron. So like this we need to take. So the sequence of energy states in order of increasing energy of the orbitals of a multi-electron atom is in the following order. So while filling the electrons in the different orbitals in an atom, we need to follow the order like this: first 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p. So this is the energy level, increasing order of energy of the orbitals. As we go from left to right, energy of the orbitals increases. So in general, we may write this order like this: 1s for simplified view, 1s, 2s, 2p for n equal to 2, for n equal to 3, shells and subshells. For this is the n equal to 1 shell, there is only one subshell, and n equal to 2, there are 2 subshells, and n equal to 3, 3s, 3p, 3d. 3 subshells will be there, spd. So these subshells also indicates different orientations of the orbitals. And for n equal to 4, 4s, 4p, 4d, 4f, and for n equal to 5, the subshells are 5s, 5p, 5d, 5f, 5c. And then for n equal to 6, 6s, 6p, 6d, you can write like this: 6f, 6h, 6i, like this. So whenever we are filling the electrons in different orbits, so first we need to fill first orbit. So while filling electrons in different orbitals of the atom, we need to fill first orbital of the nucleus. That means if it is the nucleus, this is the first orbital, and we may denote this by first shell. So it also includes different subshells having the same energy. So this is the subshell of first orbit. There is only one subshell. So we need to fill 1s, and then we need to follow like this: 2s, and then so here while filling electrons in different orbitals of electrons of an atom, we need to follow like this. First we need to fill first orbital of the atom. That means if we consider nucleus like this for an atom, there could be first orbital. That means n equal to 1 for the first orbital. So we need to fill first shell. Only one shell is there for the first orbital. So we need to fill 1s orbital. And then we need to fill 2s orbital. And then 2p, 2p and then 3s. Need to follow this type of order, and then 3p and 4s orbitals are to be filled. 3d and then 3d, 4p, 5s, and again 4d, 5p, 6s, like this. So for example, if we need to fill the electrons in the zinc atom, the atomic number of zinc is 30. Atomic number means Z for uh, zinc atom is 30. So the electronic configuration would be like this: 1s2, 2s2, 2p6, 3s2, 3p6. So we need to follow like this: 1s orbital, and then 1s orbital, and then 2s orbital, and then 2p. After 2s, 2p, and then 3s, and after that 3p. So we need to count the number of electrons also simultaneously: 2 plus 2, 4 plus 6, 10 plus 2, 12 plus 6, 18. So 12 more electrons to be filled in different orbitals. So after 3p, we need to fill in the 4s. So the maximum number 2 electrons in the s orbital. We will again explain the maximum number of electrons in the orbitals. So after 4s, 3d. 3d. So up to here there are 12 electrons. Here 14. So 3d, 10 maximum number of electrons that can be filled in the d orbital is 10. So 2 plus 2, 4, 6, 10, 12, 18, 20, up to here 20, here 30. So this is the electronic configuration of zinc atom. So filling of electrons should be done like this. So this is the order to be followed for filling of electrons in different orbitals of an atom. So as each orbital characterized by the set of quantum numbers n, l, ml can accommodate 2 electrons having ms values +1 and -1, the electron capacity of subshell is maximum of 2 into 2l plus 1 electrons. We can fill maximum 2 into 2l plus 1, not in the subshell, in a shell. In a shell, maximum we can fill 2 into 2l plus 1 electrons. So that we can find the capacity of a shell. If there are the maximum capacity n of a shell is given by like this. So if there is a shell having principal quantum number n, the subshell having values L from 0 to n minus 1. So there are 2L plus 1 subshells. So the total number of electrons that can be in each subshell we can fill 2 electrons. So there are 2L plus 1 subshells, that means 2 into 2L plus 1 in each subshell, so that the total number of electrons in a shell could be summation of 2 into 2l plus 1 from l equal to 0 to n minus 1. So that means 2 into for l equal to 0, 2 into 0 plus 1 means 1, and for l equal to 1, 2 into 1, 2 plus 1, 3, 2 into 3, and similarly we can find like this. And again, for summation of these odd numbers, we can use the formula like this: 2 into n by 2 into 1 plus 2 into n minus 1. So if you simplify this expression, maybe n by 2, 2 to cancel here, otherwise we can do 2 to cancel here. So n plus 2n into n minus 1. That means n plus 2n square minus 2n. There is again plus also, plus n also. So the total number of electrons in a shell having principal quantum number n is given by 2n square. Okay. So that means if n equal to 4, the total number of electrons that can be filled in this shell, that means n equal to 4 means k, l, m, n. The subshell is n. So the total number of electrons that can be filled in this subshell is 2 into 4 square. 32 electrons can be filled in the orbital having n value 4. So all these electrons filling in different orbitals or different subshells can be seen in this table. For example, for n values, n equal to 1, 2, 3, 4 are given in this column, principal quantum number n value. So according to principal quantum number, we can assign the shells k, l, m, n, o, p, and the possible orbitals for n equal to 1 is only 1s. One orbital, that is 1s only. And for n equal to 2, there could be two orbitals. One is 2s and the second one is 2p. So all the orbitals can be given like this. For n equal to 3, there could be three orbitals or three subshells, 3s, 3p, 3d. So like this, for n equal to 5, 5s, 5p, 5d, 5f, 5z. And again, in each subshell, here for 1s, we can fill maximum 2 electrons, 2s2. For s orbital, we can fill maximum 2 electrons only. And p orbital, there could be again 3 subshells. In each one, we can fill 2 electrons. One is uh, with the spin up and another one is with spin down. So total 6 electrons can be filled in the p orbital. This can be denoted as px, py, pz. And again in the d orbital, you can fill maximum 10 electrons. Similarly, 1, 2, 3, 4, 1, 2, 3, 4, 5 subshells. So here also we can fill maximum 10 electrons like this. And f orbital 14, g orbital 18, h orbital 22. So in this way, the maximum number of electrons that can be filled in first orbital for n equal to 1, maximum 2 electrons can be filled. Second orbital 8, third orbital 18, fourth orbital 32, fifth orbital 50, and sixth orbital or sixth cell, we can call it as shell also, 72 electrons can be filled with n value 6. Electron configuration. So the electron configuration of atom is described using NLX. N is the principal quantum number, L is the orbital rotation, and X is the number of electrons that filled in that particular shell orbital. So, for example, if we take the sodium atom, sodium atomic number Z equal to 11. So we can fill like this: 1s2, 2s2, 2p6, 3s1. We also see zinc zinc electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. So this is the electronic configuration of zinc atom. So the total number of electrons in the zinc atom are 30. So here electrons are completely filled in the outer orbital also. Outer orbital here is the fourth orbital, and is 4 is the maximum for this particular atom, three, not the 3. So in this case, for sodium atom, 1s2, 2s2, 2p6, 3s1. So up to third orbital, electrons are filled. And again, the third orbital S is not completely filled. So if the orbital outermost, this is also called outermost orbital or valency orbital. So if this orbital is completely filled, outermost orbital is completely filled, then it is said to be closed. So a subshell that contains its full quota of electrons is said to be closed or completely filled. Thus, the K shell and N shell of sodium atom are closed. Here, if you see, this is n equal to 1 means K shell. K shell is completely filled, and L shell. L shell means 2s to 2p6 is also completely filled. But the third shell or M shell is partially filled. It is not completely filled. In general, we can write up to 3s to 3p6 and 3d. D also. So this is the uh, electron number that can be filled in the third orbit. But here we are using up to 3s1. So it is partially filled. So the 3s subshell of M shell contains only one electron and is half filled. Even if we talk about subshell, it is not even subshell is also not completely filled. It is also half filled. The completely filled shells and subshells of atoms are stable. One more rule, that is, if the cell or subshell is completely filled, then we can say the atom is strongly or stable atom. And even and it is not readily disturbed. Can not disturb the atom. It is highly stable atom. And even it is half filled also. Even the atom subshells or shells are half filled, then also stability increases compared to uh, incomplete, incompletely filled shells or subshells. So the electrons in the outer shell will be in position to interact with similar electrons in the surrounding environment of the uh, substance. And again, the number of such electrons determines the valency of the atom, and it also determines the chemical behavior of the element. Not only chemical behavior, even to determine the properties, even it is chemical, optical, mechanical, uh, thermal, any properties of the substance can be determined by the electronic structure of atoms within the substance. So the material property depends on the electronic structure of the atoms contained in the substance. So electronic structure of atom is very important to identify material or to identify the property of the material. So these are the references followed for the preparation of this lecture. Thank you all.
Like, share, and subscribe. Hit the bell icon for more updates.